So transformer having there are two different type of major losses. Okay, that is called, first one is called copper loss and second one is iron loss. Transformer is having mainly two types of losses, major losses. Minor losses also there, but we have to concentrating on my major losses. So on the major losses, their losses are divided into two losses, that is called copper losses and iron losses. Copper losses and iron losses. Okay, copper losses and iron losses. The copper losses because of transformer winding. Copper losses, that is called I square R losses. Okay, I square R losses. So why? Because the transformer is having some winding resistance. Transformer is having some winding resistance, practical transformer. That's why, so we'll get some losses because of winding resistance. That losses are called I square into R. Okay, that losses is called I square into R. That is called copper losses. So generally, so why this given a name copper loss means generally the transformer winding is made by copper. Okay, generally transformer winding is made by copper. That's why they are given a name as copper losses. Okay, 99%. So transformer winding is made by copper only. So that's why copper winding. That's why they are given a name as copper losses. Okay, so that copper loss is nothing but I square loss R losses. Okay, this copper losses, I square R losses means the current. For example, if the load current is increases, okay, that means IL square into R. The current flowing into the winding is called IL square into R. That means the copper loss depends on load. The load is increasing, the winding current is increasing, and then the winding resistance is constant. It is not changing. At the time of manufacturing stage, the winding resistance is fixed, but at the operating stage, copper winding resistance of the transformer winding is same. Copper resistance of the winding is same. So once the design is fixed, design is over, the resistance cannot be changed. Not possible to change. Once the design is over, the resistance is not possible to change. So that's why the copper losses are depending on load. If the load is changing, current is changing, then I square R loss is also changing. Okay, under no load condition, copper losses are almost zero. Okay, so iron losses, the iron losses are so because of transformer core. Okay, if the transformer core is having high hysteresis, so then it will get hysteresis loss. The transformer winding, the transformer winding is not properly designed. That is called transformer core is not properly designed means the in between the two transformer sheets strips. So there is some insulation. So if insulation is not properly, so what means you will get eddy current loss. Okay, understood. Transformer is made by different type of silicon strips. Okay, this one strip and this another strip. Okay, so not a single solid conductor. No? It is a so different type of strips are placed together, and each strip is insulated by some insulation, separated by some insulation. This is called this one strip and another strip. In between these two, some amount of insulation is there. No? So if insulation is well, okay, the eddy current losses will be less. Practically, eddy current losses is not equal to zero. Okay, ideally zero, but practically at least some minimum amount of current eddy current losses are there. Okay, so this hysteresis losses because of transformer core. The transformer type of material is hysteresis losses are depending on transformer type of material. Okay, if the high permeability material, if you are using high permeability material, transformer uh, losses are less. So the transformer losses, copper losses and iron loss. The iron losses are hysteresis losses and eddy current loss. So these copper loss are depending on load. So that's why the load changes means if the load changes, that means current changes. when current is changing, that is nothing but I square into R losses changes. That means these losses are variable loss. Copper loss are variable loss, but these losses are iron losses is depending on hysteresis loop and eddy current loss. Okay, so this insulation is eddy current loss are depending on insulation. If the insulation so designed well, then eddy current loss are less, and hysteresis loss is the transformer core is designed well. The transformer core is a very good property. Then hysteresis loss are less. Okay, that means these losses are depending on voltage. So this is losses. So try to consider one by one. As the electrical transformer is an active device, you know well, the mechanical loss of transformer normally does not come to picture. Because of the transformer is a static device, there is no rotating parts. That's why does not coming to picture. That is called mechanical loss are in a transformer is zero. So only electrical losses. Okay, as the electrical transformer is a static device, the mechanical losses in a transformer is does not coming to picture. Okay, that means frictional losses. There is no frictional losses. There is no windage losses in a transformer because of this static device. Okay, it generally considers only electrical losses in a transformer. Okay, so that electrical losses are nothing but copper losses and iron loss. Okay, losses in any machine is broadly defined the difference between input power and output power. You know well. Okay, next when input power is supplied by the primary transformer. Okay, when the input power is supplied to the primary transformer, some portion of that power is used to compensate the core loss in a transformer. Okay, so because of these losses, some amount of power is wasted. Okay, so because of if the more number of if the losses is more, the output is will be less. Okay, when input power supplied to the primary transformer, some portion of the power is used to compensate the core loss in a transformer. That is called hysteresis loss in a transformer and eddy current losses in a transformer core. Hysteresis loss in a transformer and eddy current loss in transformer core. These both losses in a transformer core only. Okay, so these losses are consuming some power. So that's why the input power is not equal to output power exactly, but practically, but ideally both are same. Okay, some amount of power is wasted in the transformer core. Okay, so some portion of the input power is lost as I square or loss. Okay, I square or loss, that means winding across the winding. Current flowing the winding is called current I. So the loss is called I square or loss. It is dissipated as the heat in primary and secondary windings. Okay, because of winding resistance, these losses are coming into picture. Okay, because these windings have some internal resistance. Okay, so that is called R. And then, so because of winding resistance only, the current is, this losses are coming into picture. Copper loss. If the winding is resistance is very less, then losses are less. Okay, the first one is called core loss and or iron loss. Core loss or iron loss. Okay, in a transformer, and latter is known as ohmic loss or copper loss in a transformer. Core loss is also called as iron loss. The iron loss takes place in core of the transformer. Generally, the transformer core is designed by some iron material, general transformer. That's why they are given a name as iron transformer. Iron losses. Okay, that losses are called core loss. Actually, these losses are takes place in transformer core. That's why this called as core loss. So latter known as ohmic loss or copper loss in transformer. Ohmic loss. So ohmic loss means I square loss, copper loss. Okay. Another loss occurs in a transformer is known as Strelo loss. So Strelo loss is because of external field, external electric field, external disturbances. Okay. So these are minor losses. Okay. These are very minor losses due to stray fluxes linked with the mechanical structure and winding conductors. Okay. Stray fluxes. That means external external field fluxes. External field is interacting on the transformer winding, transformer flux. So then actual fluxes may be a disturbance in the actual flux. Because of that, these losses are coming to picture. Stray loss. Okay, mechanical structure and winding conductors. Then copper losses. Copper losses are mainly due to electrical resistance of the primary and secondary winding. You know well. I square R losses. Copper losses because of winding. So I square R losses. Transformer losses are mainly due to the electrical resistance that is called primary and secondary winding. Primary winding is having some resistance, and secondary winding is also some having resistance. Okay, because of that winding resistance, the loss coming to that is called I square R loss. Most of the transformer coils are made with copper wire. Okay, which has resistance in ohms. You know well, I'm already explained. Transformer winding is made by copper. That's why they're named given a name as copper losses. As having some winding resistance, because of that, losses are coming to it. The resistance opposes the magnetizing current flowing through them. Okay, that's magnetizing current. If the magnetizing current is reduced, okay, so the output of the transformer is very less. When load is connected to the transformer secondary winding, large electrical current flow through both primary and secondary winding. You know well. So when load is connected, but that means the load current is increases. Okay, if the load is more, the current drawn from the supply is more. Okay, if the more number of fans are connected to the load of the fans are connected to secondary side of the transformer. Okay, or more number of fans or TVs or coolers, fridges. If the more number of devices or loads are connected to the secondary side of transformer, so at that case, the load appliances are draws more current from the transformer. That means secondary current is increases. That means primary current also increases. If the load current is increasing, that I square all losses. Transformer increases and the losses will be dissipated in the form of heat. That's why the transformer temperature is increases. It's clear. Generally, copper loss are vary with the load current being almost zero at no load. Okay, under no load condition, the load current is zero. That's called I2 is zero. If I2 is equal to zero, then similarly I1 is equal to zero. That's called only no load current. The no load current is only 3 to 5% of the full load current. That is very, very small. So because of that, no load current, no load loss of the transformer, that's the copper loss almost zero. Okay, generally copper loss are very with the load current being almost zero at no load current. Because of no load current is very less. Because of that, the copper loss are zero at under no load condition. At maximum full load, when current flows at maximum. A transformer volt ampere rating can be increased by better design and transformer construction to reduce the core and copper loss. Okay, this transformer volt ampere rating, that is called rating of the transformer, is measured in terms of VA, volt ampere. Okay, the transformer rating indicated as VA. So if KVA, kilovolts, and kiloamps, kilo KVA. If it's kilo VA, if it's MVA, megavolts. For example, operating voltage in the range of megavolts, that's the transformer rating maybe in MVA. Okay, so for small size transformer, VA, volt amperes. For medium size transformer, KVA. For large transformer, MVA. Okay, transformer with high voltage and current requires conductors large cross section to help them minimize the copper loss. You know well, R is equal to rho L by A. Okay, you know well, resistance R is equal to rho L by A. If the cross section area of the conductor is high, the resistance is less. Okay, based on that, copper loss can be reduced. Okay, next iron losses. You know well, iron losses are two does, then hysteresis loss and eddy current loss. Hysteresis loss and eddy current loss are both depend upon magnetic properties of the material. Understood? Hysteresis loss and eddy current loss are both depend upon magnetic property of the material used to construct the core of the transformer and its design. Okay, simple. So by reading itself, you can easily understand. Okay, so these losses in transformers are fixed and do not depend upon the load current. Understood? These losses are not depending on load current. These losses are depends on construction and properties of magnetic material. Okay, hysteresis loss and eddy current loss depend upon magnetic properties of the material. Okay, and used to construct the core of the transformer and design. So that's why these losses are not depending on load current. Okay, even though load current is changing, decreasing and increasing, these iron losses are not changing. Okay, iron losses are not depending on load current. It's depending on voltage only. Supply voltage is almost constant in a transformer. So supply voltage is nothing but 230 volts for single phase. 230 volts. There is a for single phase 230 volts is constant supply voltage. For three phase 440 volts, that is three phase 440 volts, that is also constant. Supply voltage is constant, but load current changes. So when the load current changes, iron loss also, iron loss constant, copper loss are changing. Okay. So core loss are under transformer, which alternatively known as iron losses in a transformer, okay, can be considered as a constant for all range of load. Okay, it is not changing depending on load. It's constant. So core loss in a transformer, which is alternatively known as iron losses. Core loss, iron loss are same. So can be considered as constant for all range of loads. Okay, it's clear. So then hysteresis losses. So hysteresis losses, the work was done by the magnetizing force against the internal friction of the molecules of the magnet. I'm already explained under BH curve. Okay, so the work was done by magnetizing force against the internal friction of the molecules of the magnet to produce heat. This energy which was wasted in the form of heat due to hysteresis called hysteresis loss. This is the definition of hysteresis loss. Okay, so work was done by the magnetizing force against the internal friction of the molecules of the magnet. Okay, so that is because of that producing heat. Okay, this energy was wasted in the form of heat due to hysteresis called hysteresis loss. So this concept are you know well. When the magnetic material magnetization force is applied, the molecules of the magnetic materials are aligned in a particular direction. You know well. Okay, whenever the transformer core is subjected to the alternating magnetic flux, so for for particular direction, the magnetic materials are aligned in one particular direction. And when this magnetic force is reversed in the opposite direction, so because of we are giving a AC supply for one direction, the magnetic domains are arranged in one particular direction. Okay, the magnetic materials are arranged in a aligned in a particular direction. The domains are arranged in one particular direction for one half cycle. For another half cycle, the force is changed. Force is reversed in opposite direction. So the internal friction of the molecular magnets opposes the reversal of the magnet, result in magnetic hysteresis. Okay. Therefore, the core loss are made of material with narrow hysteresis loops. Okay, the narrow hysteresis loops, so that little energy will be wasted in the transformer in the form of heat. Okay, the transformer, well, the BH curve. Okay, so if the transformer from the BH curve, well, so this is called BH curve. No? So first increases, then coming to here, and then like this. Okay, so this is called BH curve. This is called B, this is called H. Well. So if the narrow hysteresis loop means, so if the transformer core, the hysteresis loop is like this. Okay. Okay, the core of the transformer core is made of material with narrow hysteresis loop. Okay, narrow hysteresis loop, so that the little energy will be wasted in the transformer heat. Little energy is wasted in the transformer in the form of heat. Okay. So this is called so one of the formula, hysteresis loss equation. So very important, hysteresis loss in a transformer. Okay, hysteresis loss in a transformer. So very important this formula. So based on this, some problems are there. Okay, numerical problems. Try to consider all. Hysteresis loss is equal to Kh into F into Bm for 1.6 watts. So this is the equation, hysteresis loss coefficient. Kh is called hysteresis constant. Okay. So WH is equal to, that is called hysteresis loss, is equal to Kh into F into Bm for 1.6. Here Bm is called magnetic flux density. Magnetic flux density. Bm is called magnetic flux density. Okay. Kh is called hysteresis loss constant. Okay. That means hysteresis loss is proportional to the frequency and magnetic flux density. No? This hysteresis loss is proportional to the frequency and magnetic flux density, that is called Bm. Am I right? And then eddy current losses. So whenever a conductor is moving in a magnetic field or conductor is placed in a changing magnetic field, an EMF induced in the conductor according to the Faraday's law. Well. Whenever a conductor is moving in a magnetic field or conductor is placed in changing magnetic field, an EMF induced in the conductor according to the Faraday's law. Understood? You know, well, this is the principle. Whenever a current carrying conductor is placed in a stationary magnetic field, it experiences force according to the. So for motor, for transformer there is no rotating partner. That means transformer winding is stationary. In a transformer winding stationary, but the current is alternating. The flux is alternating. Okay, change in magnetic field. Okay, conductors are stationary. That's why this is called statically induced EMF. Transformer, the transformer winding EMF will be developed. That is E1 and E2 is called statically induced EMF. Okay, but in motors and generators are dynamically induced EMF. Okay, because of the conductors are moving in a motor or generator, but in a transformer, conductors are stationary, but magnetic field is changing. That's called flux is changing. That's why this is called field is the induced EMF is called statically induced EMF. Okay. So this EMF is set up in corresponding to the induced currents. These currents circulate in the large number of small concentric path within the solid mass of the conductor are known as eddy currents. Okay. This EMF set up corresponding induced current. These currents circulate in the large number of small concentric path within the solid mass of the conductor is known as eddy current loss. Okay, understood. So like this. If you are using solid conductor, solid type core, in that case, this large amount of current is circulating in the solid type material. Okay, so large amount of current, that is called I, circulating in the transformer winding. If this transformer core is designed by only one single core, or the single solid cylinder, solid type core material. Solid type core material. If you are designed a transformer core is solid type material, so in that case, we will get like this. So if this transformer core is designed by with strips, okay, it's made by different type of strips. Okay, so in that case, this the eddy current losses. This current is circulated in the transformer core is very, very less. Okay, this current is not circulating into here, and this is not circulating into here. So because of that, the current is in the circulating is very, very less. Okay, as the eddy currents are not used for doing any useful work and flow within the body. Okay, this current is not useful to the transformer. Okay, this current cause power loss in the transformer core. Okay, the power loss due to the eddy current is called eddy current loss. Understood? The EMF setup in the corresponding induced currents. First, this transformer winding is placed in transformer core is placed in alternating magnetic field. So because of the transformer core is subject to the change in magnetic flux. So because of that small amount of current is passing in through the winding, transformer core, and this transformer current is circulating in the inside of the transformer core. So if the circulating currents are more, so because of that there is a eddy current loss are more, but here circulating currents are very less. But in so in this within the region only. So these losses are very, very less. So that's why they were laminated core. So the eddy current losses are very less. So this is the formula for eddy current losses. Okay. This is the formula for eddy current losses in a transformer core. So eddy current loss is equal to Ke into F square Ke. Eddy current constant into F square into Kf square into Bm square watts. Okay. Understood. The Hysteresis law, it is called eddy current loss. Hysteresis loss is proportional to the frequency. So Bm for 1.6. And eddy current loss is proportional to the frequency square and Bm square. Magnetic flux density square and frequency square. The Ke, Kf are constant. So eddy current loss are proportional to the frequency square and Bm square. But eddy hysteresis loss are depending on so frequency and Bm for 1.6. Okay. So this is losses in a transformer. So efficiency in transformer. So well, efficiency is nothing but output by input. Okay, output by input. Input is nothing but output plus losses. Okay, a transformer is a static device, means that there is no friction or windage loss. There is no rotating parts. No, that's why these friction and windage loss are zero. Okay, the transformer has a losses called as copper losses and iron loss. Copper losses and iron loss. These two losses, transformer losses, nothing but copper loss and iron loss. But generally, these losses are quite small. copper loss also, and also I square R loss. Okay, copper losses are generally it's called as I square R losses. Then efficiency is equal to output power by input power. Efficiency of the transformer is nothing but output power by input power, then into 100%, 100 into percentage. It's called efficiency, percentage of it. Then output power is nothing but input power minus losses is called output power. So we can write, we read it like this manner. Output power is nothing but input power minus losses. Otherwise, efficiency is equal to output power by output power plus losses. Input power plus output power by output power plus losses is also called as efficiency. So then change this, re-modify that, the 1 minus loss the input power 200. This is called transformer efficiency. And voltage regulation. So next, voltage regulation is nothing but the change in voltage from no load to full load is called regulation of the transformer. Okay. So voltage regulation is the percentage of voltage difference between no load and full load is voltage of transformer with respect to the full load is called regulation. Regulation of the regulation is nothing but just to consider. This is the definition. Voltage regulation is the percentage of voltage difference between no load to full load voltages of a transformer with respect to the full load is called voltage regulation of transformer. Voltage regulation is equal to, this is called no load voltage. E2 is called no load voltage. V2 is called full load voltage with respect to full load. It's called regulation of the transformer. That is with no load to full load. Changing voltage from no load to full load is called so regulation of the transformer. Okay, this is about regulation of the transformer.